Okay, so we have looked at the operation of the DC generator, and we understand this problem of armature reaction. So we need some sort of solution that overcomes the armature reaction, and that's what section 411 is. 411 is titled commutating poles. So what it's done to eliminate, not entirely, but mostly, this armature reaction effect is to incorporate something called commutating poles into the physical design of the DC generator. Now, what that's going to do for us is it's going to sort of recenter, so to speak, the neutral zone, so that the operation of the DC generator is maximized when we have a load connected to it. Now, these things are called commutating poles. They're also referred to as interpoles. And depending on the text that you're looking at, you could see them referenced either way. And something else that I would mention to you is, sometimes in schematics with the labeling, you'll see interpoles instead of commutating poles. And as a matter of fact, I think we'll see that in one of our labs coming up. We'll see this use of the term interpoles versus commutating poles, but just understand it's the same thing. So let's look in detail at how the commutating poles work to lessen the effects of armature reaction. So what we're looking at here in figure 416 are the commutating poles, and we see two of these. Normally, you would have a pair of commutating poles to match each pair of regular magnetic poles, that's producing the flux that we utilize, okay? And so these are, it says, placed in between the main poles, and they carry a winding that is in series with the armature. And we can see that here, okay? So if I follow out brush X here, we can see this coil of wire that's wrapped around this pole, and here's the negative brush here. And we can see that any current that's flowing through the armature is also going to flow through these coils of wire that are wrapped around the commutating poles. So what happens, and notice sort of the detail here, let me erase some stuff so we can see it better. But what you can see here, if you look in the detail of the figure here, here is magnomotive force or magnetic flux, and it's MMF sub C, okay? And that's the magnomotive force that's created by the commutating poles when current passes through that coil. And then you have the other MMF, which is the armature flux. And of course, this is what occurs when we connect a load to this DC machine, and the current starts to flow through all the conductors, and this was the flux from the armature. All right, now without going into a lot of specific detail, but just to show you, even though this may be obvious, we can see that the line from the magnomotive force from the commutating pole is in this direction, and we also see it in that continued direction below here, right? And what this does, and what it's showing in the diagram, is it is in direct opposition to this armature flux. Okay, and so we learned in the earlier videos that the armature flux was the thing that was causing this pole tip saturation. It was also causing a shifting of the neutral zone. And that was a big problem for us in the operation of this DC generator. So what's neat about this, among other things, is, we have a load that's connected, out here to the brushes. So if the load increases and the current through the commutating poles, it will increase in proportion to the load increase, right? At the same time, you know, the current in the armature conductors is going to increase. And so there's sort of this feedback going on to where, you know, the load increases, this armature conductor current increases, you know, through all these conductors, but at the same time, the current through the commutating poles also is connected, since the way of the, as we see through the design, everything runs through the brushes, right? So it sort of regulates itself in the sense that the load increases, this armature flux increases, but at the same time, this commutating flux increases, and it increases in direct opposition to the armature flux, and it tends to neutralize that. And the effect of the neutralization is that the DC generator runs the way that we need it to, much more efficiently, and without this sparking and arcing and all that results from the armature reaction. Now, he says the neutralization is restricted to the narrow brush zone where the commutation takes place. The distorted flux distribution under the main poles, unfortunately, remains the same. So, you know, it's not perfect in its solution, but it's it does allow this machine to operate, you know, in a usable manner, and it's you know, it's the solution, design solution to the armature reaction problem.